Hi everybody, this is Professor Chang of Bukkyung National University, and welcome to my class of image processing. Today we are going to talk about spatial filters. Okay, now what is filters? Now what is spatial? Maybe you have no knowledge. So let's start from the concept of filters. Okay, now you are here, and we have many things to do in this semester. Okay, so most of you may have an image of filter like this, right? There is a coffee beans, and you pour hot water, and if you don't have filter, and you pour the water, then all the mixed beans, grained beans and waters, coffees are mixed here. But if we have filter here in the middle, then the grains, the beans, coffee beans left upper side and coffees are coming out through the filter. You see? So this is a very similar idea when we are using filter to the data. There are lots of data and lots of different data, and we put this data into filter. Then some part of data coming out through this filter. This is what we are talking about today. So we are putting data to the filter, right? And because this is not data processing class, this is image processing class, the data we are putting in the filter is the images. So we put images into filter and we got some result. And this result is not the original image. Something was missing, was taken out from the original image, and the part of images are left. Then how we are going to separate what we want to be left and what we want to be removed? How can we separate them? So that is the design of the filter, and we are going to study about that in this class, today's class. There are two sorts of filters. One is spatial filters, and the other is frequency-based filters. Okay, spatial filters is what we are talking about today. Is the filter according to the pixel values and change in a spatial space. You may know what the spatial means. This is what we see in the real world, x, y axis. So you see my image and you see this slice. There is an x-axis and y-axis. You can see the difference of colors according to the x-axis and y-axis, and that is what we call a spatial space. So some images changes according to these spatial spaces. For example, there is a filter. This filter the color of this filter is black, right? And the background is white. So when you see the changes of these colors, according to the x-axis here, then the colors are white, and it suddenly changes to black, right? And then it again changes into white here. So you see the color changes. This is what happens in spatial spaces. Okay, then this is I didn't explain what the spatial filter is exactly yet, but after you learn it, then you can easily calculate it. Not really easy, but you can calculate. So if you can add and multiply and sum, and if you know what is multiplying numbers and what is the add operation, then you can calculate it. So that is spatial filter. Another filter is frequency-based filter. Okay, frequency-based filters are the filters according to the values and changes in a frequency space. The frequency means the high frequency and low frequency. Maybe you may have heard about what the frequency is. When you hear my voice, okay, my voice is a little bit lower than some other people. Okay, students or professors may have high frequency voices, or if you see singers, soprano singers, then you may hear that okay, their voice frequency is pretty high, right? And if you hear some guys who has a very low frequency like this, then you may hear that some low frequency. And when you hear if you listen to music, then the low frequency means the low level scores like do, re, mi. That is low frequency, and sol, la, si, do. Okay, that is a higher frequency. So that is what happens in. I explained the frequency in sounds, but it is very similar when you are talking about frequency in images. Some images changes very frequently. That is, the colors change very frequently, not frequently, but sharply. That is, we call that. That is the high frequency, and if colors changes very slowly, then we call that is low frequency. Okay, that maybe we have more time to talk about the frequency filters later, but today we are going to talk about spatial filters more. Okay, there are many sorts of spatial filters. Okay, this is the edge detection what we can do with the spatial filter. This is the left image is the original image, and the right side image is the processed image, filtered image. Here you can see the edge part is emphasized and left, but the other part, colors or the colors information of the other parts are removed, right? It becomes overlap. Okay. This is another filters, smoothing. We can use the mean filter or Gaussian filters, or there are many other filters for smoothing. Okay. If we apply the smoothing from the original image to original image, then we can see this kind of images. Right? You may see what the difference is. Okay, there are also min-max filter. This is also spatial filters. Okay, spatial filter. The min-max filter is the same word of the morphology. You have studied dilation and erosion last week. Okay, that is what we. If we apply that in the generalized version, then that we call that min-max filter. Erosion is this maximum filter, and then dilation is going to be this minimum filter. Okay. Then min-max filter, we can apply the min-max filter in color images. So if this is the original image, and when you apply the max filter, then it becomes like this. And then min filter, if you apply, then it becomes like this. So you see the differences, right? When you apply the max filter, then it becomes, there are informations, all the informations between in the images is emphasized here, right? It's not removed. The color differences left, but it becomes wider because white values are bigger. Okay, this is max values and max filters, and this is min filter. If we apply min filters, then it becomes darker, right? And informations are much removed here. Okay. Okay, min-max filters can be applied, are often used in these days for deep learning. You may have heard about deep learning, right? AI and deep learning. And in deep learning, especially for convolutional neural networks, these min-max filters are very often used inside of the network structure. So this is not the deep learning class, so I do not explain about the max filters in deep learning, but if you have interest, then you may search in the internet, and you may easily find how the max filter are used in deep learning. You may search it max pooling in Google or other portal sites, and you may find it easily. Okay, there are another filters. We say that convolutional filters. Actually, except the min-max filter, smoothing and edge detections are convolutional filters. The convolutional filters are general version of edge detection and smoothing. So let me explain about the convolutions. Okay, convolution is the calculation between two matrices. Okay, you may think that this is an image. Okay, bigger one. This is an image, and you want to multiply, and you want not multiply. You want to convolve. You want to apply convolutions between this original image and the filter matrix. So here, the size of the filter matrix is 3 by 3, okay, from A00 to A22. And the original image size here is 6 by 6. Usually, this size is bigger, maybe 512, 512, or 1024 and 1024, yeah, and much bigger in these days, right? But for the easier explain, I put here only 6 by 6 here. Okay. This is a matrix calculation. So after this calculation, you may have this size of image and this size of matrix. So let's see how it is calculated. Okay, this is an equation per equation, and if you understand this equation, then you can skip the the left part of this lecture. But okay, let me explain it easily without the equation. Okay, so we want to calculate this pixel. Okay, so we want to calculate the 6 by 6 matrices. Okay, this is the result. Then if we know how to calculate a pixel value here, then you can apply this into the same process to the other pixels, right? So let's start from a pixel here. Okay, to calculate this pixel, you have to know this matrix, sub-matrices. Okay, you see the position of C22 and the B22 here, the same position, right? And then you may box it with neighbors, with its neighbors, right here. And then this box is same to the size of this box is same to the filter box. Okay, if the filter box size of the filter is bigger than this, now it is 3 by 3 and it can be bigger, maybe 5 by 5. Then when you are boxing here, and this box should be bigger, so 5 by 5. Okay. Anyway, here is this is the simplest case. Okay, so to calculate the C22, and you need to sum matrix over here from B11 to B33. And you may calculate convolution between this filter matrix and this submatrix. Okay. Then here you may calculate it. You may multiply element wise. Okay, which means you may calculate A00 multiply B. This is 00, and A01 multiply B01, and plus A02 multiply B02 plus A01 plus B01. A01 multiply B01, 10, plus A11 multiply and A11, and So not multiplying A00 to B00. This is B11, right? So because this position, now we are calculating C22, so the center point here is B22. So here, the left upper part here, B index of B is B11 and B12, B13. So we may multiply A00 to B11 and add plus A01 multiply by B12 and plus, and multiply A02 and B13 and plus. So you may calculate this operation until the A22 and B33 and add all. That is if you write my explanation into the equation, it becomes like this. Okay, so yeah. Okay, sorry, this was Korean, but it was the same. Sorry that this is written as Korean, but the contents are the same as the previous. So please forget about please ignore these Koreans. Okay, so here, okay, this is the same. To calculate C22, and you need to calculate multiply element wise between two matrices here, right? And this is called zero padding. Okay, let me write here. Okay, zero padding. Okay. Add zero padding means add zeros. Okay, in the border. Okay, so this is because to calculate the zero, this is to calculate C00, because to calculate C00 we need to multiply we need to do elemental wise multiplication. Okay, but if you make the box here around the B00, then there are no values outside of here. So we assume all the values here are zeros. Okay, then when you calculate elemental, if you do calculation from C00 to C55, then you may have all the values of the convolution. Okay. Here I say that this is the convolution in the image processing, a simplified version, because the original convolution operation includes the flipped operation inside. So before calculating the multiplication between two sub-matrices, two matrices. Original convolution operations has the flip of the one of the matrix. So here you may flip the filter matrix, then you may multiply element-wise. So, but in image processing, this flip is removed because it can be easily ignored mathematically when you design the filter. So this is the simplified version. Okay, this was the convolutions. Convolutions are widely used in computer vision and image processing to extract features and to enhance the quality of images. When you are using the convolutions in the images, for the image, and which means that we consider the images into the matrix. The gray images are appeared in 2D. We can consider gray images as the 2D matrix and the color images as the 3D matrix, because in gray images we have the intensity values for each pixel, and in color images we have color information for each pixel, which means RGB. So we have three values for one pixel. So this becomes 3D matrix. Okay. So these convolutions are utilized for deep learning as well. I told you that the max filter or min filter can be used, often used in deep learning, and these convolutions are one of the main core of the deep learning in these days. We say the deep learning academically as a convolutional neural network. That is one type of model of deep learning. Convolutional neural network, we say that CNN, convolution, right here. So inside of the convolutional neural network, CNN, and we use lots of convolutions. Okay, using the convolutions, we can change the images into the new form of the images. Here, I told you that this is the edge detection is available with the filter, and this can be done with the convolution of this filter. Okay, if you use this matrix and apply the convolution, then you get this image. Okay. Also, you can use this filter, and if you apply this filter to an image, then you may have the smooth image here. So all the filter results are what I explained in the beginning of this class can be done with these filters. Okay. So except min-max filter. Okay, if you want to do max edge detection, then you can do this kind of filters. Okay. First two filters, we call them as Sobel filters, and then the third one here is the Laplacian filter. You can make this size of the filter bigger. Okay, this is 3 by 3, but you can make it bigger, and there are matrices, number of values for the matrices for the filters already in internet. You may search it. I can get it easily. Okay, this is the smoothing. Okay, you may multiply. You can use, if you use these filters to an original image, then you may have the smooth image. Okay, you see the sum of the value here is the 1, so which means if you apply this filter to original image, the intensity does not change. Okay, here this is a Gaussian filter. Okay, the left one is the mean filter, and the right side here is the Gaussian filter. And if you add all the values in a Gaussian filter, you may understood. You can note here all the sum of these values are 1. In the edge filters case, if you add all the values here, you can recognize that the sum of all the values here are 0, right? Yeah. This is what we need to design the edge detection filters. Okay. Also, we can design other convolution filters. Okay. These are the numbers and values of the filters are designed by computer scientists long time ago, but you can design your own filters and you can apply your filters. Actually, when you are using the filters convolutions in deep learning, the deep learning algorithm find automatically the values. Deep learning algorithm automatically find the values, filter values, when they learn the images. Okay, then this is the last part. Why do we use these filters? Okay, this is as you know, this original image has been changed into edge image by a filter, by software filter. Okay, then why do we have to do this? This is because we want to reduce the amount of the information. In the original image, we have lots of informations, and there are color informations here, there are lots of informations here, right? The color changes here. This is more brighter, and this is darker, even in the same object, right? But in the processed image, the information has been reduced a lot. All the color information has been removed, and only the edge informations are left. Okay, then amount of information has been reduced. Then why do we want to reduce this information? Because this is very related to the difficulty of the problem. If the size of the information is big, then it's difficult to understand for us. If I give you a test, okay? If I give you a test in 10 minutes, and if I give you a book, okay? Let me see. Okay, this is a book, right? This is a book. This is a Python book, okay? And if I give you a test in 10 minutes, and all the exams are coming from this book, and your scores and your grades will be very dependent to the test. If I say that, you'll be crazy, right? Because it is almost difficult, very impossible to study all the information inside of this book. This is very big. But if I give you a test from a page, a one-page script of today's class, then you will be, okay, I don't like maybe you may say that, oh, I don't like the exam, but it is understandable because today's contents are very small, okay? I can study in 10 minutes, okay? If the size of the information is small, then it is easy to understand. And this is not only for human, but this is also same for the computer. Okay, if you have lots of data, and if you just put lots of data unprocessed to a computer, then it's very difficult to understand. But if you give the processed data and the small data and very important data, then it is easier for the computer to understand. Okay, some of you may think, oh no, professor, this is the era of deep learning and era of big data. If we have more data, we are more happier. Okay, that is true. But I'm talking about not the number of the data. Yeah, okay. If we have lots of images to train the machine learning model, then it is fine. It's very good if you have lots of data. But size of the image, if the size of the image is too big, maybe 4K quality of image, then it is very difficult to run all the data with 4K data. And then but in 4K image, lots of data in the image may not be necessary and may not be required to run deep learning. So if we can reduce and if we can remove all the unimportant data, then it is very easy to understand. So not just reducing the size of the information, but we want to extract more and more important informations left. Okay, you understand? Big data is good, right? Big data is good. But we only say that big data is necessary, then big data of important information is necessary. Okay. So, but it is also up to purposes. For example, this is there is an original image and also the edge detected images. According to the edge detection algorithms and filters, we may have a different result. Okay, then when you see the information of A, okay, you know, if you know the person, then you can recognize who he is. Okay, maybe who she is, I can sure, but okay, we have lots of information, so we can know who he is. But in image B, what can you know? We have a knowledge. Okay, this may be a person. Okay, human face. Then that's what we can know, right? So this is up to purpose. If our purpose is to recognize whether this object, this image is about human face or not, then these edge images are enough. Okay, but if our purpose is to understand, to recognize who he is, if our purpose is to identify the person, then this edge image, this processed image is not important, not good for us. So it's up to purpose. So, but if our purpose is just to recognize whether this is a person or not, then the image of A has redundant information, isn't it? So according to your purpose, if your purpose is if your purpose requires small information, and then make the data into smaller, okay, we can do it with filters. Okay, so that was about the filters. Okay, today we talked about the filters and spatial filters and convolutions and convolution and filters. And lastly, we talked why we do use filters. What was that? To reduce the information and to extract more important information. Okay, thank you very much and see you next week.